Hello, everyone. It's me again. Today we are going back to Unit 7, which is on atomic theory. So remember before spring break, we started on this unit. We started off talking about the history of atom, right? So remember we talked about how the atoms, the model of the atom has evolved from, let's say, being just a solid ball. Um, and all the way to the model proposed by Bohr, which is like, there are different shells and electrons go around different shells around the nucleus. Okay, so today we are getting into the theory of quantum mechanics. Basically, this is the currently accepted model of an atom. Okay, so since Bohr, there were a couple extra addition to the model of the atom. And one of the key contributor, as you guys may remember, it's just one second, right here, Schrodinger. Okay, so today's the model that we're going to talk about today, and this is the currently accepted model of the atom. It's um, mostly came from Schrodinger. So here, as you can see, we have like really complicated equations, really crazy looking model of the atom, which we'll get into today as well. Um, Now, the theory of quantum mechanics is actually way beyond the scope of this course, and it's actually, really, really complicated. You will be taking like several courses on just quantum mechanics if you get into chemistry. So we are not getting into that, but we'll just briefly touch on how this model is a couple key things that are different from Bohr's model. So just quick review on Bohr's model. Like remember, you guys learned about how to draw the Bohr's model, and we did you did this since like grade 8, grade 9, and also did it also in grade 10. But this is the Bohr's model is not accurate. Okay, so it's not really how the atom looks like. So think about when we talked about the Bohr's model, it looks you think about having electrons going around the nucleus in different orbits. Okay, so here we have orbits, right? We talked about we have first shell, it's not orbitals, that's something we'll get into a bit later. But orbits, we have first shell, second shell, and third shell, and so on, like different energy levels. And we talked about, first shell, it can be hold 2 electrons. Second shell, it can be hold maximum 8 electrons. So you guys have probably remember the magic number like 2, 8, 8, and 18, and so on, right? For the Bohr's model. Okay, but that's this is not the accurate model of an atom. Okay, so a couple of things that we notice for for a couple addition to the Bohr's model. One of the things that it's called quantum. Okay, so that's why this theory is called quantum. So quantum is basically defined by the definition of the energy difference between two energy levels. Okay, so this is quantum. So you just think of it as like a packet. Okay, um, quantum, you can think of it like an easier word, packet. So it's a packet of energy between two levels. So we notice that for example and the electrons when it's get excited, it can get jump to a higher energy level. Okay, so this is when um, electrons get excited, get absorbs energy, and it can move from one energy to the next energy level. Okay, and now opposite, like once it loses the energy, it can go back to its ground level. Okay, so when it get excited, it jump all the way from level 1 to level 4, but the energy can get emitted. Okay, so when it emits the energy, like loses the energy, um, it, it goes back to the ground level. Okay, so when for basically the energy difference here from energy level 1 to energy level 4, we call this quantum. Okay, so it doesn't matter which level to which level, but as long as it's the difference between one level to another level, we call it the quantum. Okay, so it's just the energy difference between one level to the other level. So that's one additional thing that we notice adding to the Bort's model. And the evidence to that to the quantum, we see the quantum in energy is when we observe different gases. So here I'm not going to detail here, but you know, you guys probably remember like different um, elements. Okay, when you have light go through the prism and pass through these either gas or elements, they have a unique fingerprint. Okay, so this fingerprint is called the line spectrum. So for example, here, you know, for hydrogen, like how we find out, like say a star is made up of mostly hydrogen, is when we see all these distinctive lines of these of hydrogen gas. So we'll see like a distinctive red and green and blue and purple right here. Okay, and this is observed when, you know, like same thing, like electrons get excited, and when it jump from one level to another level, and when it emits the energy, when the electron emits the energy, it goes back to a lower energy level. And when it goes back to the lower energy level, we can observe those certain colors. So we see all the purple, blue, and green and red for hydrogen gas. Okay, so this is again the packet of energy, and we call it quantum. Okay, so that's the first thing that's added to the Bort's model. Um, Now, second thing, it's instead of orbits, you know how, you know, we think of the Bort's model as like, you know, the solar system, like different planets is going around the sun. So that's like the nucleus, and it's everything. It's two-dimensional. Okay, so for the newest model, the currently accepted model of the atom, there are we don't think of electrons circulating in orbits. Okay, so it's not a plane, it's not a two-dimensional um, a plane. Instead, electrons are found to be occupying in a region of space. Okay, so instead of thinking 2Ds, you guys now have to move on thinking about how like electrons are actually going around the nucleus in a three-dimensional space. Okay, so electrons are occupying in a region of space, and we don't call it the orbits. Orbit is like 2D, is like a ring, but it's we call them orbitals. Okay, now according to this new model, it's impossible, okay, to know the precise location of the electron. And so like here, you know, if you look at the Bort's model, you see all these dots like going around the circle, right? But now instead of thinking dots, you need to think about like a spherical shape that go around the nucleus, and we cannot pinpoint where the electrons might be. Okay, but instead we can only be able to know the probabilities. Okay, so probability abilities of finding the electrons in a certain specific region. Okay, so that's why Schrodinger has all those complicated equations. Those equations are used to calculate the probabilities of the where you can find those electrons. Okay, so again, this is very important because this is the model that we'll be using. It's no longer 3Ds, I mean 2Ds, it's 3Ds. So here I'm going to just quickly show you this model here. We have all these fancy orbitals. So again, these circles are not rings. They are like a spherical shape or different type of shapes in a three-dimensional space. Okay, so um, now we're just gonna talk about the orbital shapes here. There are four types of orbitals. Okay, so I'm gonna give it here. I made up, not me, but some other teachers made up a short form of memorizing the four types of orbitals. Okay, so some pilots don't fly. Yeah, maybe, I don't know, but we just, someone just made this up. Especially during this time, I guess lots of pilots got laid off. So some pilots don't fly. So the four types of orbits are S orbitals, so some S orbitals, P orbitals, D orbitals, and F orbitals. Okay, so the S orbitals, S easiest to stand for sphere. So it's a spherical shape. So notice here we have the axis. We have X, Y, Z axis. So normally when you do math, like when you plot a graph, you have the X, Y axis, right? Okay, so that's like a three-dimensional space. I mean, two-dimensional space where you graph something. But later on, when you get higher in level in math, you might get into drawing something in 3D as well. So here that's where the third axis can come in. So this is the Z axis. Okay, so it doesn't matter how you oriented the X and Y and Z, but they are just basically perpendicular to each other. Okay, and X Y is perpendicular to each other, and then you can think of the Z axis just pointing out towards you. Okay, so three axes, you're able to draw a spherical shape. And the second types of orbital is called the p orbitals. Now p orbitals are there are three of them. Okay, three p orbitals, and the shape of the p orbitals, you can just think of it as a double lobe. Double lobe. Okay, and there are three of them. There's the px, py, and pz. Okay, so like for example, this one here on the x-axis, so it looks like a double lobe here. Okay, like this. So that's the px right here. Okay, and this one on the y-axis, we have the py, and this one oriented along the z-axis, that's the pz. Okay, so I know it gets kind of weird, but hang in there, we're almost there. And for the d orbitals, there are five of them. I don't expect you to be able to draw these ones, but just remember that there are 5D orbitals. That's all I need you to remember. Okay, so if you take a look at the D orbitals, they have four lobes instead of double lobes for the p orbitals. For the D orbitals, they have four of them. Okay, so here we have four of them. Like this is called the D X and Z, and there's D, X and Y, and so on. But again, you don't need to know the name of them. But there are four of them that look like a quadruple lobe, and there is one that look like kind of a weird shape like this. Okay, but again, you just need to know there are five of them. Okay, and lastly, for the F orbital, it gets really complicated, and you don't need to know these ones. Okay, you don't need to know, you don't need to draw them, and there are seven of them, but you don't need to know. Okay, just give you extra information. There are seven of them. Okay, so I'm just gonna pause here and move on, and you guys can take a break. I know this is a lot of weird information. So some pilots don't fly. So for the model of the atom, there are four different types of orbitals, and they give you the probability of where you find the electrons. Okay, they have the highest probability of finding the electrons. That's what they are. So we'll continue the next slide. You guys can take a break and come back. Okay, let's continue here. So the first slide, we talked about quantum mechanics, which is the currently accepted model of the atom. And for this model, it's basically there are two key changes. So basically, instead of 2D, it's 3D. So we call them orbitals, and they are basically location of the electrons. And based on the probability of finding them, there's highest probability of finding these electrons within a region of space. So it's 3D, and we call them orbitals. Okay, so instead of orbits, now we call them orbitals. Now, I just want to introduce these two terms. The ground state is when the electrons are not excited, they are in their lowest energy state. Okay, and sometimes when electrons get excited by absorbing energy, electrons can transfer to a higher energy level called excited state, so which we'll get to these two terminology later in the package. So for this package is separate from the previous one. So on OneNote, you guys should have printed off the single sheet plus two sheets and plus this package. This package has 8 pages. Okay, so we'll talk about the first four pages today, and then we'll continue next class. Okay, so quantum mechanics. So now instead of thinking about like there are rings go around the nucleus, we used to call them shells, right? In the Bohr's model, now we are going to call them energy level. Okay, so it's very like similar to the Bohr. Like we have the lowest energy level closest to the nucleus, and we have the higher energy level away from the nucleus. So this energy level we call it N. Okay, and it has a very special name based on the theory of this model. Is called quantum number. Okay, so quantum number 1, 2, 3, 4, 5, and so on. Okay, so that's the energy level of all the electrons, where electrons are located. And based on this energy level, we can also calculate how many different types of orbitals there are. Okay, so the equation is very simple. It's just n squared. Okay, so basically for the first energy level, first shell, just think of it as first shell. It's if you plug in 1, n is 1, 1 square is equal to 1. Okay, so at the energy level number 1, there is only one type of orbital. Okay, and the orbital is s. So remember the order of the orbitals that we talked about the previous slide. Some pilots don't fly, so the first type of orbital is the spherical shape. They call the s orbital. Okay, so there's energy level 1, so that's why I put the 1 here, and the orbital we have at this level is a sphere, 1s. Okay, so if you think of it as, take a look at the picture down here, we have the nucleus in the center of the atom, right? And basically at energy level 1, used to be shell, right? Just a ring, but now you just think of it as a spherical shape. So I'm just gonna just use these dot, 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 dot to represent it's a spherical shape, not a, not a ring, but it's a three-dimensional region of space. Okay, so this is the 1s orbital. Okay, and it's the lowest energy level, is closest to the nucleus. Okay, so that's the 1s orbital. Now that's energy level 2 back here. So if you plug in 2 into n, so 2 squared is equal to 4. So that means at energy level 2, there are 4 different types, not different type, but 4 different orbitals. Okay, so this number gives you the number of orbitals. So what are they? So they are energy level 2, right? So we always start with the s orbital. So there are energy level 2, 2s, and then we have all the p orbitals. So we have the 2p. Remember p orbitals? There are 3 types: px, 2py, and 2pz. Okay, so now what you need to think about is at the second energy level, there are these 3 types of orbitals. Okay, so now I'm just gonna let's just imagine here in this picture here, the middle one here, again, the nucleus and in the center. Now the 2s, this is 2s orbital, is a bigger sphere than the 1s. Okay, so take a look at the 1s much smaller, and the 2s is bigger, and the 1s is basically inside the 2s. It's just they overlap each other. Okay, so the 2s orbital is just a bigger region of space um, away from the nucleus. So again, you have to think 3D. Okay, so if you think about cutting this in a cross section right here, you will see the 1s orbital right inside, and the 2s orbital, its overlap is covering this entire region. Okay, covering overlapping the 1s as well. So that's the 2s. Okay, and you don't need to know this term node. Basically, that's where the 1s and 2s overlap each other, but that's again, it's too much detail for you to know. So 1s, 2s, that's how basically is a region of space where we expected to find the electrons. Okay, but we don't know where they are, but they are. This is where we can find them. Okay, and then now the px and py and pz, and remember from last where's the did I oh I oh somehow I did not scan the second page here, but you guys have it. You guys have the px and py and pz. So if you want me to add to it, I can add on it to here as well. So for example, the px would be a double lobe right here, added to here, and the pz would be added to here, and the z axis is right here. Okay, so it looks very nice, like a little flower. So that those are so on this picture here we have the 1s orbital, we have the 2s orbital, and we have the 2px, 2py, 2pz orbital all in on this atom. Okay, so that's basically, again, what the heck is this? This look like a weird flower to me, right? But basically on these are the region of space where you expect to find electrons. So for example, you won't be expecting to find electrons here because that's not the region of space where from the orbital, okay? But instead, you're expected to find the electrons here, could be here, could be here, could be anywhere in this region of space, okay? So just think 3D. So now let's move on to energy level 3. So as you may expect it, the number gets much bigger. So 3 square is 9. So there are 9 different orbitals. And so we start always with s orbital, 3s. And then we have the 3px, 3py, and 3pz. So that's 4. And we're going to add to the 5d orbitals. Okay, so remember the 5, no, not the 5, not the 5d, but there are 5 of the d orbitals. Okay, so d orbitals from the previous sheet we just talked about, there are 5 of them. Okay, so just think of it like here we have 4, right? And then plus the 5 of them, then that's 9. Okay, so 9 different orbitals. Just going to erase that. And lastly, again, I don't expect you to know all these, but 4 square is 16. So there are 16 different orbitals. So we can do the math quickly here. We have the 4s, and we have the 4px, 4py, and 4pz plus the 5 of d orbitals, and then remember we have the 7 of the f orbitals. Okay, so 4 plus 5 plus 7, that's exactly 16. Okay, so don't worry about all these for now, and it'll get easier, trust me. Okay, so those are the orbitals. Now, the key thing that you're going to get out from this package is how you're going to feel electrons on this on all these complicated, weird-looking orbitals. Okay, so remember in the Bohr's diagram, you guys know how to fill those diagrams, right? You start with first shell is 2 electrons, second shell is 8, and then move on to 8, and then 18, and so on. But now we are going to fill in all these orbitals, all these 1s, 2s, 3s orbitals, and how we put electrons in these orbitals. Okay, so a couple things to talk about. Other rules we're going to use to talk about. So here on the top of this is page 3, I think. Yeah, page 3. Electron configuration. So this term electron configuration is just a fancy term to basically ask you to fill electrons into the orbitals. Okay, so we call that electron configuration. um, so couple things to remember for each orbital. So we have all these 1s, 2s, and 3px, 3py. Each orbital can maximum hold 2 electrons. Okay, and for the electrons, they must be placed in orbit, like in order for them to fit together nicely, they need to have different opposite electron spin orientation. Okay, so here they must have opposite electron spin orientation. So here I use 2 arrows and one up, one down. That's how we represent electrons spins. Okay, so they have to be opposite to each other. Otherwise, because remember electrons, they like to repel each other. So in order for them to kind of get along, they need to have these opposite spin orientation. Okay, so here just analogy. I'm going to have you guys to read it and talk about why electrons has to be one spin up, one spin down. But again, it's just something to remember. Okay, just an analogy for you to kind of remember. Um, so here on this table here is just the summary of what we just talked about. Um, N energy level, and then the number of orbitals. And so we talked about the energy level 1 only has 1 orbital, right? So because each orbital only fits maximum 2 electrons, so in orbital 1, it can hold maximum 2 electrons right here. Okay, and for the energy level 2, so there are 4 orbitals, so 4 times 2, because each one holds 2, so maximum of electrons it can have in second energy level is 8. Okay, and again, you don't really need to memorize these numbers because you will get you know how you will be able to figure out as we go. Okay, so this is just how these number came from. I don't need you to know the Pauli exclusive principle. That gets a little too deep. Okay, so here, let's focus on this part, mechanics of filling, how to assign electrons into atom. Okay, so here are the steps. So step number 1, you're going to determine the electrons, number of electrons in the atom. Okay, so you just need to figure out using the atomic number. We assume that is neutral. So say carbon has 6 protons, then it must have 6 electrons. Okay, so that's easy. Determine the number of electrons. And we're going to always start with the first energy level, and then the second, and then the third, and so on, just like how you feel the board diagram. Okay, and once we and then we always going to go with the order of some pilot don't fly. So for example, the second energy level, there is the s and p orbitals, so the s always goes first, and then the p's, okay, and then the d's, and then the f, and so on. So that's how the order of filling the electrons. And lastly, this is another rule that you need to remember. It's when these are the px, py, pz, they have a special name called degenerate orbitals. So like the p orbitals, there are 3 different types, px, p, and py, and pz. And for these orbitals, the rule of filling these orbitals are you have to only get 1 electrons into one of these 3 orbitals before they pair up. Okay, so this is what I mean. So for example, if this is px, Py, and Pz. So to fill electrons into these orbitals, you have to fill in 1 on each one of the orbital first, okay? And then it can be double up like this. And remember, one spin up, one spin down, okay? So they have to be in opposite spin to avoid electron-electron repulsion, okay? So an analogy to think of this is to think about a bus. There are many seats. They're all empty. So usually when we try to when we get onto the bus, we go onto a single seat, right? Like, instead of try to sit with people, we usually go on a single seat, and then before all this empty seat goes out, and we start to double up. Okay, so that's exactly how the degenerate orbital works. If there are 5 of them, then they all go singly on each one of them before they pair up. Okay, so a lot of talk so far. Now let's get into action. Let's actually start to do some work, do some filling of electrons. So we're going to follow these 4 steps. Okay, so I will have the page. You can always refer back to page 3 for the rules. So step number 1, we are going to figure out the number of electrons. So carbon, remember carbon is 6, right? So that means carbon has 6 electrons. Okay, so here, I know this is um, not something that you can remember right away, but just want to remind you, these are the orbital, the order of the orbital. So we start with the, so just imagine that, let's say if the nucleus is here, so we start off with the 1s orbital, right? And then the 1s, 2s, and then now with the 2p's. And don't forget the p's, we have the px, py, and pz. That's why there are 3 lines here. Each line represent an orbital, okay? And then we have the 3s, 3p. Now here comes something that's a little bit weird. We have the 4s, okay, before the 3d. So this is something that I'll get back to you a little bit later, but we just, you just have to remember the d orbitals is actually, the 3d orbitals, they're actually at a higher energy level than 4s, okay, just something to remember. So I will show you guys a way to memorize the order of these, um, the order of the orbitals, but it's you will get there. But for now, they are there for you to follow. Okay, so carbon 6 electrons. So we're going to start with the first. Oh, that's the first rule. Second rule is first energy level are filled first. Okay, so we have the 1s. That's only one orbital, so we're going to have one arrow up, one arrow down to represent the 2 electrons. Okay, so we use up 2, still 4 more. And then the second energy level, we have the s orbitals, so we're going to fill in the s first. So that's 2. So that means 6 minus 4, we have 2 more to go. So remember the rule number 4 is if there are degenerate orbitals like px, py, and pz, you have to fill in 1 into each one of the p orbitals first. So I will have the one here, one goes to the px, and one goes to the py. Okay, so 6 arrows represent 6 electrons. So I'm done, okay, for the carbon. Okay, so I'm going to have you guys, why don't you guys take a moment to just pause the video right here, okay, and then do the nitrogen and oxygen, okay, and then you come back and check your work. So I hope you guys have no problem doing this, but just quickly go over the answers. So nitrogen has 7 electrons, right? So 2 in the 1s, 2 in the 2s, and then I have 3 more. So 3 of them go into each one of the p orbitals, px, py, and pz. Okay, and oxygen has 8 electrons, so that means it's just 1 more than nitrogen. So that's 3 here, and then last one, they had to be double up with the px. Okay, and that's it for carbon, nitrogen, and oxygen. So here I'm just going to have you guys to do the rest of this page for homework exercise A. And then I actually will do one more thing with you. So the rest of this page, fill electrons using arrows, one up and one down. And then so for example, hydrogen has one, so you only need an arrow one for hydrogen. Okay. Now let's move on to the next page because I just want to go over a little bit more with you. So there's actually so what we just doing on the previous page is called a longhand electron configuration. As you can see, like, if the atom has a lot of electrons, it will just, take forever to fill in all the arrows, right? So that's called a longhand method. And there's a shorter way to do that. It's called the condensed electron configuration. Okay, so for example, the ones that we just did for carbon, nitrogen, and oxygen, I'm not going to repeat here. Instead of writing arrows, so here actually I'm going to do this one. 1s2, so there are two here, and then there are two here, right? 6 electrons for carbon. So instead of writing arrows, we can write a shorter way like this, okay? So we call this, so here, this number here, it's basically the number of electrons in that orbital. So for example, here 1s, there are 2 electrons. So the 2 here, it's not a square, it's 2. We call it 1s2. Okay, and here we have 2 in the 2s orbital, so this 2s2. Okay, for the p orbitals, there are 2 electrons here, so 2p2. Okay, so that's how we can shorten the way of, instead of drawing arrows. So what I want you guys to do is for homework, other than filling arrows on this page, I'm going to ask you to add the condensed spell here, the condensed electron configuration on the side. Okay. So for example, hydrogen, it's basically 1s1. Okay, so the line gets too long. Electron configuration. I can't spell today. Configuration. Okay, so for hydrogen, I want you to just write down 1s1. Okay, maybe I should do one more just in case some people are confused. For example, let me try to do, let's see, I can do neon with you. Actually, let's not do neon. Let's do, I can do sodium. So Na, okay, so Na, we have 11 electrons, right? So you're going to start with 2 electrons on the first orbital, 2 electrons on the second orbital, right? And then I'm going to have, I can fill up all 6, but the way to fill it is always single and then double like this. And then now, so that's a total of 10, okay? So that means I have one more in the 3s orbital, okay? So on the side here, I'm going to ask you guys to add the condensed way. So I have 1s2, 2s2, 2p6. Okay, you don't have to list x and y and z, just combine them together. And then 3s1. Okay, so that's all today. I hope the electron configuration part is not hard. You guys will get the hang of it. Just review everything I talked about. If you want to read the textbook a little bit, I will assign the page number, and also I will assign the Hampton textbook if you want extra examples and whatnot. Okay, and then just for homework, just finish all the electron configuration on this page, and don't worry about the rest of this package because I do want to go over with you. So just stop right here, okay? Just stop at the end of this page. And then, yeah, review all the orbitals. I know it gets really weird what to think now. Think about the px, like py and pz, and all the s and d, and all the different types of orbitals. I have shared some pictures with you like this, so I want you guys to, just take a look at, think about, oh, these are the s orbitals, these are the p's, and these are how p's are together, right? These are the d orbitals and f orbitals. So look through the pages on under this unit, and I also posted some videos for you. So if you have time, watch the video as well. Okay, so I will talk to you guys next class. Bye.